So, hello guys and welcome to a new video. We will continue solving equations involving the integer part of x or the floor function of x. So, we want to solve now the following equation. As you can see, we have x to the power 2. So, it looks like an equation of the second degree in x, but the problem is we have this integer part of x. So this is the thing that is making it much more difficult than it looks like. So we want to get rid of this integer part of x and transform this to something we know how to deal with. So we are going to use the definition of the integer part of x. So since the integer part of x lies in this interval according to its definition, then now by multiplying the double inequality by minus 10, then I get this. And by adding to the double inequality 3x squared plus 3, so I want to get this expression, so we get the following double inequality. And as you can see in the middle, we have our equation, so we can substitute the middle term here by 0 because this is our equation. So we have this double inequality with 0 in the middle, which this double inequality transforms into two inequalities. The first one is 3x squared minus 10x plus 3 less than or equal to 0. And the second one is 3x squared minus 10x plus 13, which is strictly greater than 0. And those two inequalities have to be satisfied at the same time. So we're going to study both of them, and we begin with the latter one. So I call the first inequality 1 and the second 2, and I start looking at 2. And with a little bit of algebra, we can rewrite this in this way, and we can see that this is strictly greater than 0 for all x, for all real x. So for all real x, this is strictly greater than 0. So I mean, there's nothing to do here. It's already strictly greater than 0. Now, by going back to the inequality number 1, since this is, the left-hand side here is a second degree polynomial, so we know that we can factorize it. And I mean, this is no match for u. So it is factorized in this way. And we want it less than or equal to 0. And this holds whenever x lies in this interval. So now this double inequality has transformed into this. But are we done yet? No, we are not. There's still some work to do here. So now, since x belongs to this interval, then the possible values of the integer part of x are 0, 1, 2, and 3. And you can see, so you can see that in this interval we have 3 integers, 1, 2, and 3, and 0 has to be taken with because of the definition of the integer part of x. So since x belongs to this interval, the possible values of the integer part of x are 0, 1, 2, or 3, And we have now to study each one of these cases. So if the integer part of x is equal to 0, going back to our initial equation, we will get 3x squared plus 3 is equal to 0, which gives x squared plus 1 is equal to 0. But we know that this equation is unsolvable in the set of real numbers. So this is impossible here, which means that if the integer part of x is 0, our equation has no solutions. Okay? Now, if the integer part of x is 1, then substituting in our original equation, we get this, which gives us x squared is equal to 7/3. And since x is positive, remember that x belongs to this interval, so it's positive, then x is equal to the square root of 7/3. And we have to check that the integer part of the square root of 7/3 is actually 1, and it is. So this is a solution. So in the same way, if the integer part of x is equal to 2, substituting in the original equation, so we get to x equal the square root of 17/3, and we have to check that the integer part of this number is 2, which it is. So this is another solution. And last but not least, if the integer part of x is 3, then substituting in the original equation, we get that x is equal to 3, which already is an integer. So to sum up now, the solutions to our original equation are the square root of 7/3, the square root of 17/3, and 3. So thanks guys for watching, and see you in the next video.